I just want to introduce Michael Wellman, who is the next speaker. Michael Wellman is Lynn A. Conway Collegiate Professor of Computer Science and Engineering at the University of Michigan. He received a PhD from MIT in 1988 for his work in qualitative probabilistic reasoning and the decision-theoretic planning. For the past 30 years, his research has focused on computational market mechanisms and game-theoretic reasoning methods with applications in electronic commerce, finance, and cybersecurity. As Chief Market Technologist for TradingDynamics Incorporated, he designed configurable auction technology for dynamic business-to-business commerce. Wellman previously served as chair of the ACM Special Interest Group on electronic commerce and as an executive editor of the Journal of Artificial Intelligence Research. He is a fellow of the Association for the Advancement of Artificial Intelligence and the Association for Computing Machinery. Welcome, Michael Wellman.
Thank you. So this session is about evaluation of advanced AI in interactive or multi-agent settings. I'm going to be presenting a view of how we think about that in my research group, the Strategic Reasoning Group at the University of Michigan. And in particular, I'll be presenting a framework, which we call the metagame evaluation framework, that we find useful for this. I'll also be talking about our empirical game-theoretic analysis approach. We'll have a case study of bargaining scenarios, but I will want to view this as mainly not specifically to present those results, but as a vehicle for thinking through some of the issues that come up in this kind of evaluation. Please don't hesitate throughout to ask any clarifying questions or challenge any egregious statements I make, but let's go ahead. So the problem of evaluating advanced AIs, we want to assess the performance, despite the fact these are complex and learning systems or learned systems, and they're going to be interacting with each other and humans in a variety of environments. There's a couple of major areas of complication. One is just the inherent stochasticism of learning systems and what that means for the uncertainty of what behavior they're going to have when it's actually deployed. And the one that comes up particularly for multi-agent systems is the strategic context, and I'll have more to say about that in just a moment. But just for the uncertainty, this is an issue that comes up in trying to evaluate learning systems in single-agent settings as well. Here's a plot that comes from the PPO paper, which is one of the most cited papers in AI, where the practice is if you're going to, you can't just run your learning system and then see what the result is. You have to try it at a variety of different random seeds and try to quantify the uncertainty of the performance that you get. And that's all pretty well understood in its common practice. How to deal with the strategic issues, though, I think is much less understood, or there's certainly less consensus about dealing with it. The issue is that how your agent performs will depend on what all the other agents in the world are doing. That is the other agent context. Now, presumably, during learning, the designers had some assumption about what the other agents would be doing. But often that assumption is very opaque. It may be inconsistent. And even if it is transparent and consistent, it could be wrong. And we need to deal with that. And you can't deal with it by just saying, well, we'll just deal with the worst case, or a Byzantine assumption, because that's always going to be so pessimistic. To take the example from Eugene's presentation before, the pessimistic Byzantine assumption for traffic is that other cars are just going to come right at you, all over the time, and there's nothing you can do in that setting. So that's not going to work. You have to try to think about which are the other agent contexts which are actually plausible. There's uncertainty about it, so you have to be able to be robust to them, but be specifically geared toward the ones that are more likely to occur. Which ones are more salient? So this often naturally, in multi-agent reinforcement learning, we often think of recognize that in the multi-agent context, what we're essentially in is a game situation. And so a lot of multi-agent reinforcement learning is done in a setting where you just think about the problem as game solving. To what extent does the multi-agent system, do you learn an equilibrium of the game? And you need to measure how close you are to an equilibrium. So these are charts from one of the papers from my group, from my student Max Smith from a couple years ago. The specifics are not too important, but basically what it shows is how over time the learning system converges toward an equilibrium measured by regret. I'll show you a formula a little bit. Regret is a property of a strategy profile. So in a multi-agent learning system, what is learned is a profile or a set of policies for all the agents. And the regret of that is how much an agent could benefit by deviating from that. So if regret is 0, you're in a Nash equilibrium, and so it's a measure of how close you are to equilibrium. Okay. Now how to measure the regret in a complex learned system is a challenge. If there's multiple equilibria, which there generally are in a general sum setting, how do you deal with that? And also whether it's even right to be thinking of this as game solving is a question. So we're not going to be satisfied with just this. Okay. And even recognize to evaluate a particular strategy in a profile, again, that depends on what the other agents are doing. So one solution or one approach you could take is to say the strategic context that I care about is the context when the other agents are rational in some sense. Say they're playing a Nash equilibrium, sigma star. So the Nash equilibrium regret of a policy is just how much you lose by playing that policy instead of the equilibrium policy against that equilibrium. Okay, so that's got to be a positive value. So this is basically a measure you could use if you were willing to make the assumption that the relevant other agent context is equilibrium play. Now, I'll make a little bit of a digression. And I think it was during Vince Konitzer's talk, somebody asked about, this might be good for RL, but for LLMs, they're not really rational, and we can maybe get cooperation, in that kind of setting. Let me make a claim that it's often good to start from the assumption that your other agents are rational. Not that you necessarily believe that assumption, but you could, make an assumption that the other agents are smart, and if they're not as smart as you think, you'd be wrong with that. The alternative is to make an assumption that they're irrational in some way, but then what conclusions you're going to draw will depend on exactly how you think they're irrational. And moreover, that's also an assumption, and if they're differently smart, you'll get a different kind of outcome. One thing I think about is how you influence another agent. If you want to influence another agent, first you want to think about, well, how smart are they? And or how rational are they? And if they're irrational, one thing you can do to influence their behavior is trick them. That's the approach you take to influencing non-rational agents. If the agents are rational, you can't trick them, but you can incentivize them. And I like to imagine a world where the approach we would prefer to be taking is to incentivize the agents to do the right thing, as opposed to always thinking about how's the best way to trick them, which is what you're going to be doing when you are modeling them as irrational. Okay, so this is our particular definition, Nash equilibrium regret. There was also a paper by Balduzzi and colleagues a few years ago that presented this, and they used the term Nash averaging. So in case you've heard that, it's the same thing exactly. Now, notice that the definition is relative to a particular Nash equilibrium sigma star. So if there are multiple equilibria, you're going to get different measures depending on which one. And that's actually a problem or issue. Balduzzi suggested taking the maximum entropy Nash equilibrium, but one could have other bases for selecting, but also recognizing that you're going to be sensitive to that. Okay, this is just one measure. The domain that I'm going to use as a example throughout is a two-player bargaining game, sequential bargaining game. Here's a picture from, there was a paper a few years back that called this game Deal or No Deal. It's actually been used in lots of of studies in AI in recent years. There's a set of items of different types. There's T different types and some number of each of those types that the two players have to divide up. And they have valuations for those types. They each have different valuations. Each player knows its own valuation, and there's a distribution of what the other agent's valuation could be. They proceed through alternating offers. So player one says, I will propose to divide them up this way, and player two can then accept that, or say, no, but I will counter-propose this other way of dividing them up, back and forth until either a deal is made. If one of them accepts the offer, that's a deal. They've divided them up. Or you could reach the horizon and not have a deal. It's an imperfect information game. It's quite challenging to solve analytically. The number of information sets grows enormously with the horizon and the dimensionality of the types. But anyway, that's the setting. It's a general sum game, and I think it's a very good test bed for kind of cooperation in a mixed motive scenario, because both players want to reach a deal. There's usually going to be deals that are mutually beneficial for them, but of course they care which deal they get, and they have an incentive to understand something about what the other player wants, because that way they can make effective offers that will actually be agreed to that divide up the items. Okay? Any questions about the setup? Yes. Is this like a turn-based setting, so the leader presents the... Yeah, there's two players, player one and player two. Player one goes first, player two responds, then player one, then player two in a series of rounds. Is it played for a long time or just once? Is it played for a long? So this is the game as defined is a one-shot game, but of course there has a number of rounds. Number of rounds of going back and forth in making offers and counteroffers before that's a deadline. And we generally also assume that there's a discount rate so that they would prefer to reach a deal earlier than later. Okay? Great. So we can take a multi-agent learning approach to deriving a policy for this game, and or any game, and I'm going to refer to an algorithm for doing that as a multi-agent training algorithm, or MATA. A MATA takes a game environment, typically will be represented by a simulator, plus a random seed. That little thing there is supposed to be a seed. And what it produces is a profile of strategies, one for each player, in this case 2 players. Okay, represented, say, as a neural network. So a MATA is a meta strategy in that it maps games to strategies for playing that game, right? And presumably a multi-agent RL algorithm can derive policies for any environment that they're placed in, okay? So these are meta strategies. Well, if we have meta strategies, then we can define a meta game among those strategies. So in the meta game, the rows and the columns, instead of being policies for playing a particular game, they're MATAs. They're algorithms for learning how to play games. The payoff entries here would be the expectation over the random seeds or over the games that they could be playing, because it could be asked to play. Okay, and we can analyze this metagame as a way to evaluate the agents. Okay, let me make a little bit of a digression to say how will we fill in the payoffs value here. This is within our approach that in my research group we've been developing actually for about 20 years now, called empirical game-theoretic analysis. Also in Vince Conister's presentation yesterday, he polled the audience and said, how many of you are familiar with game theory? And almost everyone raised their hand. My guess is that most of you have encountered game theory as a theoretical device, or as a set of concepts and machinery and definitions. EGTA is motivated by trying to make it practical as a way to analyze multi-agent systems as in arbitrary complexity. Analytic game theory has quite strict limits as to how tractable it is to both write down and solve the games you care about. But it's often quite simple to define a game in terms of an agent-based model, an agent-based simulation model. That's the same kind of definition that reinforcement learning uses for how you represent an environment. That is, you have a procedural description of the game, not an analytic form. But given that procedural description, we can use empirical methods, sampling, machine learning, statistics, to characterize the strategic properties of the solutions to this game. So the way this typically works is that we selectively explore a strategy space and a profile space over those strategies. We use the simulator to get data about what happens when different strategies play against each other. And we use that to induce a game model, perhaps using some machine learning techniques or just estimating the payoffs in each cell. It's typically an iterative approach where we start by simulating some strategy profiles. We induce that empirical game. We analyze that game that may help us think about new strategies we would want to add. That's why I refer to it here as a model-based method, because you're producing a game model that you're continually enriching by more simulation, more learning, more strategies, and ultimately going to get the conclusions about it that you want. Some of you may have heard of a multi-agent reinforcement learning algorithm called PSRO. How many of you have heard of PSRO? Okay, a minority. PSRO stands for Policy Space Response Oracles, for whatever reason. This was a method that was introduced by DeepMind about 8 years ago, and it's really become it's a version of EGTA, and it's really the most popular framework these days for using it. Okay, so I mentioned that we also care about quantifying uncertainty. Well, we can do that in the metagame by careful management of how we associate our simulation results with particular random seeds. So remember, we have a game defined by modders playing against modders. We can sample some random seeds. We use that to estimate a game. And then we can analyze that game to get some statistic of interest. NE regret would be an example of a statistic of interest. I'll give some more later. And then we can sample another one. So we try this random seeds, we try some more. We get different readings of the statistic, and ultimately we get a distribution over these statistics, and that tells us what we care about. Okay, there's another cartoon to show this maybe a little bit better. We can get a confidence interval on NE regret as follows. We have our estimated game. So here I'm showing agents playing each other, and the data is written in the cells. We can solve that game for a Nash equilibrium, say sigma here. Then we resample that by from each cell, we resample the data with replacement to put in a new game, and we measure the regret of our solution to the original game in this resampled game, and that gives us one data point on the bootstrap distribution. How many of you know about bootstrap statistics? A few. If I can make one recommendation, learn about the bootstrap statistics. It's a way to be able to apply statistical analysis to your results without having to know anything about particular analytic distributions or anything like that. It's based on resampling and other kinds of things. There's a great book by Dennis Shasha called "Statistics is Easy!" And it is. Okay. So anyway, that's the bootstrap. Okay, so as I already mentioned, one candidate for a metric would be Nash equilibrium regret. Another one, that is very different. They don't even have to be numbers. Statistics can be graphs. So the best response graph for a game, we can replace the values in the cells by just putting a 1 in the column. That's the best response for each row. Here's rock, paper, scissors, a game you all know. And the best response graph, of course, is a cycle on the right. But if we calculate the best response graph for many resampled games, we'll get a number between 0 and 1 in every cell, which is an average it basically tells you the frequency of being a best response. Okay, so actually what motivated this, the work on the metagame framework was originated by my former student Lynn A, who is now at DeepMind. He had a particular idea for a new multi-agent reinforcement learning method, which I don't have to go into the details here, but that motivated, it was the first motivation for doing this study. We were also particularly interested in looking at how much decision time search can improve policies, or does it always improve policies? Okay, I'm not going to go through the results here, but we took a whole set of state-of-the-art multi-agent RL algorithms, and here is the ranking of them, and for a particular version of this bargaining game, and here they're ranked by any regret, and so here RNAD, that was the that's regularized Nash dynamics. This was the algorithm that DeepMind used to get the milestone on Stratego a few years back. That ended up at the top, and in particular the search-enhanced version of it. And if you look on the list, you see actually we had each algorithm had a search-enhanced version of it, and that always was a policy improver. One other observation we get from looking at the best response graph statistic on this. First thing is that there's no dominant meta strategy. Again, I know you can't read the print on these, but when you can eyeball this, you can see there's no just sync where everything is, something that's a better response to everything. Another thing that you see is that there's a lot of these self-edges. This was not anticipated by us, but it makes a lot of sense in retrospect that each of these algorithms has a tendency to overfit to itself. That is, remember I said, well, it's unclear what they might be assuming about the other agents. Well, it seems like implicitly they're assuming that the other agents are going to be kind of like themselves. And that's kind of natural, that's something that's available to a multi-agent training algorithm is a copy of itself. And so even the algorithms that were not so great were really good against themselves here. Okay, so that's just an example of what we learned. So our first study there was on multi-agent reinforcement learning. More recently, we've decided to try to look at metagames over large language model agents. So we can derive an agent from an LLM. We'll call that an LLM-based MADA. Lewis?
Just a quick clarificatory question. Apologies if this is stupid. If an agent's really good if an algorithm's really good against itself, isn't it also really bad against itself?
If it's really good against itself, is it also really bad against? No, these are not zero-sum games at all, right? So being good, being an effective bargain or finding win-win deals to make, that's really good.
Perfect. Thank you.
So an LLM-based MADA is also a meta strategy because they can play any game that you can describe to them in a prompt, right? You describe them to the prompt, and then you just guide them through playing the game by prompting them to give the next action based on the history. So they're also meta strategies and are also amenable to be analyzed in this way. So we tried this for the bargaining game. And this work is led by my current student, Gabe Smithline, who is also here in the summer school. And he's got a poster about this that you can find out more details that I'm not going to get to today. So again, here's the bargaining game. Here we use t equals 5. T was the number of item types, a distribution of how many, what is the quantity of each type. Also, in this case, we have an outside offer. So this is in negotiation. This is called the BATNA, the best alternative to a negotiated agreement. So each you'd rather walk away than make a really, really crummy deal. Okay, everyone has some reserve outside offer. So they have a walk action where they can end the negotiation and get their outside offer, get their BATNA. Okay, so we used 5 LLMs in this study. 2 from OpenAI, 2 from reasoning and the chain of thought and the non-chain of thought versions, also from Anthropic, Claude Sonnet, and from Google Gemini. We found pretty interesting that all of them could competently make legal moves with even the basic prompt about what the game is. This wasn't true for the open source models, the small size ones. So they were not even reasonable things to be looking at in this study. So we only had really API access to the LLMs we were studying. However, we did find that some of them made some pretty bad mistakes. So we experimented with different levels of detail we were giving in the prompt. We were very careful in our prompts not coaching them about how to play the game or what kind of, giving them an algorithm to play the game. We just wanted to describe the game and maybe underscore or emphasize some things. So prompt level 0 or circle 0, we call it, is the basic game rules. At one more circle level is we remind them that their objective is to get the best deal for themselves and what their outside option is and things like that. But I said they make some common mistakes. Let me tell you about those mistakes. An example of a basic mistake is I'm player 2, player 1 makes me an offer, and I reject that, and then I make a counteroffer that's even worse for me than what player 1 just offered me. It's hard to come up with a situation where you could say why that would be a good idea. And in fact, all of these we would consider to be basic mistakes. And so we took each of the non-chain of thought LLMs and ran them in self-play with the different circle levels to see how often they made these mistakes. And here's this 5-dimensional graph. So you can see that this particular one, OpenAI's 4.0, never made mistake 3 or 5, but it pretty often made mistake 1 or 2. And by modifying that prompt, we can maybe reduce those mistakes some amount. So that helped us choose which of the prompt. So an LLM plus a prompt circle defines a particular meta strategy. Okay. So all told, we made a game among 9 LLMs. So we had the 5 models, and we had 2 or 3 versions of some of them. It turns out the chain of thought versions of these models didn't make those basic mistakes. We didn't try those first, so that's why we had these. So those we just gave the basic prompt to. So we collected data on 3 instances of this bargaining game that had different horizons and discount factors, plus BG0, which is a mixture, so even a meta game, version of that. Okay, so we found when we measured the when we derived the max entropy Nash equilibrium of the metagame, OpenAI models were best represented in that. And here's the best response graph. And again, not to expect you could really see that, but again, we don't have any dominant strategies. And here, unlike in the reinforcement learning MATA case, we don't see the self-loops. So, maybe not surprising, these LMs were not trained specifically to play this bargaining game, and they are not overfitting to themselves. In fact, it seems that in every case, something else it plays better with that than itself would. Okay, so that was a little bit surprising and interesting. Now here's again, don't expect you to look at the numbers, but here's some more data. So in addition to looking at the regret, that's really a measure of sort of just direct performance. How effective is it at playing the bargaining game? We looked at some other measures that may be getting at more of the cooperative aspect of things. So one would be welfare. We looked at 2 versions of welfare, Nash welfare and utilitarian welfare. That's basically just a product welfare, or basically the product of the 2 payoffs or the sum of them. Here, so for regret, low is better. For the other numbers, higher is better. And again, O3 Mini, the reasoning version of the OpenAI, really seemed to be the best all across the board. We also looked at specifically a fairness measure, which you think also would be perhaps a candidate for measuring cooperation. Envy freeness up to 1 unit. How many of you know what envy freeness is? Okay, just a few. Envy freeness is a basic fairness concept that says that if an outcome is envy free, if the parties would not want to trade the outcomes they got. So if you divide up the items to make a deal, basically, if we offer to switch what we got, we wouldn't want to do it. Okay, and that makes sense because we have different valuations for the items, and if we were effective at making a deal, I got the items that I cared about the most, you got the items you cared about the most. Up to 1 unit, an issue though is that envy-free allocations don't always exist when you're talking about indivisible items. So imagine if you were dividing up an odd number of items, we had the same valuation for them, someone's going to prefer what the other one got. But envy-free up to 1 unit, if we just got rid of one of the units, that always exists. So in this case, we found that there was not, we thought it might be the case that the strategies that were best just on their own effectiveness for their own profile would be different than the ones that were best on welfare or fairness, but we didn't find that. They're the same in this case. I don't want to over interpret that. There may be other situations where that would be different, and that's why you look at multiple measures. And that's really a virtue of the metagame framework, is that at least the framework is agnostic about what measures you're looking at. I should say that here we are always measuring these in the equilibrium context. So we're asking, how does that strategy do on welfare, on fairness, when it's playing against the equilibrium? You would get a different answer if you were asking how it did in some other context. Okay. We added a new strategy, just hand-coded, a very simple strategy we call tough. Tough is a tough bargainer. It makes a minimal offer. It says, I'm going to keep all the items, all the quantity of all the items except for 1 unit of the item I like the least, and give that to you. Take it or leave it. I'm not going to budge from that. Surprisingly, this strategy was a best response to many of the LLM agents, which suggests a weakness in these LLM agents. It wasn't so much a best response to the OpenAI agents for whatever. I'm not making an advertisement for OpenAI, by the way. I have no, but that's just what we found. Now, it itself is not an equilibrium. It's not in the equilibrium very much. It's not a very effective strategy because the smart agents will just walk away from it and not deal with it. But many of the other LLMs were quite amenable to it. Okay, why were they doing that? Well, one thing we found when we looked in deeper is that they were making hallucination mistakes. Basically, it seemed when we look at the chain of thought or just the output that they give, when they see the offer, it seems so bad that I can't believe it's really what was the offer, and they assume it must have been really a better offer, and then they accept it, which was pretty interesting. Okay, so rather than talk about the yes question. Generally not. So the question was, is the minimal offer better than the outside offer? There's some probability that it could be, but it's very unlikely. If it is, but with low, it's only with low probability that it is. So in the overall game, under the certainty, it tends not to be. So it's a real mistake. So clearly the best policy against tough would be to just walk away immediately. Now you don't know you're playing against tough, so how do you implementing that might be tricky. Okay, thanks. But rather than go to the conclusions, let me go to some discussion questions that I'm going to ask you to think about. So again, just thinking about this as a case study on evaluation. I showed you some metrics, any regret, welfare measures, fairness. What other measures might you want to use to evaluate MATA, cooperativeness specifically? So let me ask that question. Also, on the bargaining side, what are the properties that we would want negotiators to have? Why are we even, would we evaluate AI negotiators? Let me say, one of the reasons we're attracted to this problem is because it seems like a very plausible use case for LLM-based agents, is to go out and have them make deals for you, go negotiate something I'm looking for. I have very general language capability. Let me go out and try to make deals. Before these are roaming around doing that, what properties do we want them to have? So let me propose the following. These 4 tables on my right, your left, are going to look at the evaluation question, talk about among yourselves. Focus on the first bullet. If you hit an impasse or a converge, you can go to the second bullet. The tables to my left here, so I guess there's 5 tables. Focus on the bargaining question. Again, the first bullet, and if you have time, the second bullet. We'll take maybe 5 minutes for that. Okay, let's turn it back. So let's hear a little bit about what you came up with. So this table. Tell me something that you thought about for metrics for evaluating cooperation.
Okay, we were a bit confused about what to use, but the one thing we could agree on was that there is a Pareto frontier, and that we should be on the Pareto frontier, otherwise something is going wrong in terms of cooperativeness. If one negotiator could actually help the other person without hurting themselves and is not, then they're probably adversarial. So that felt like a minimum requirement.
So great point. Pareto efficiency is a very appropriate measure for something like this. Now, let's be a little bit careful because, of course, this is a game of imperfect information. And so you could fail to reach a Pareto optimal deal in a given setting just because you sort of didn't have enough rounds to sort of, to find that, right? And in fact, you could even argue that, so let's also make sure we understand what that means. So a Pareto optimal division of the items would be one such that there's no other division that both of the players would prefer, right? That is something that you would want to be able to reach. That would be good, but you shouldn't expect to be able to do it all the time given the imperfect information that happens over that.
I have a very simple question.
Sure.
If we are taking turns to bargain, why are we considering like Nash and not the Stackelberg, for example? If it's like, I don't know exactly what is going to happen in the next turn. I can like.
So good question. So the question is, this is a game that you would represent as a tree, kind of an extensive form. So why are we looking at Nash equilibrium as opposed to something, well, Stackelberg is a particular thing where you assume a leader-follower setting. But even just why not look at subgame perfect solutions or things like that? Well, first of all, it's imperfect information, so that's going to be quite tricky. But also, even though the game, a particular version of the bargaining game is a game in extensive form with imperfect information, the metagame is a normal form, simultaneous move metagame. Because if what you're choosing is which LLM am I going to use, which LLM agent am I going to use, that's just a matrix game. Okay. This table here. Any other thought about metric of cooperativeness?
If the gold standard is to ultimately have humans think that it's cooperative, then what you could do is just get some amount of human labels of like which they think are cooperative, feed it into an LLM, and have it either extrapolate based on those examples, or write an essay and have it just classify for you.
Okay, so human judgments about cooperativeness. Okay, not to put you on the spot, but you're a human. How would you look at an outcome and decide whether it was cooperative or not?
That's fair. Yeah, the discussion got a little bit more beyond the specific game, and I think the challenge, it's easy in a specific game to give a formalism. It's hard to give a definition of cooperation, in my opinion. That fits all games.
Yeah, no, absolutely. So we might need different measures targeted to different classes of games of interest, perhaps. Okay, this table?
I can explain. So what we are trying to look at is if there were to be more than one agent, right? Like more than two agents, then if there were to be some disruption happening, maybe because of externality or maybe just because of one agent creating the disruption, we wanted to see how fast can you get back to the equilibrium after the disruption. Like, the more quick you do it, the better your algorithms are.
Okay, so perhaps looking at some kind of resilience or adaptiveness to other agents or invasions of new strategies or something like that. Okay, great. Anything in the back table?
So I think instead of pursuing exact Pareto optimal, we can choose to approximate to see the willingness of corporations of agents, such as how much it can willing to trade out compared to its initial offer.
I see. So you could measure something about the dynamics of the offers and seeing how much concession happened over time or things like that. Yeah, great. I think it's worth thinking about stuff like that. Moving to desiderata for AI negotiators. Let me start with this table here. Any thoughts about what you would like to see in a negotiating agent?
We discussed transparency was a topic and some sort of explainability for why the agents responded.
Transparency or explainability. So if you observed its behavior, you would then say, why did you make this offer at this time, and have a good explanation, say, of that. Or why didn't you accept this offer? Things like that. Okay, great. This table here, any properties of negotiation agents?
Yeah, I mean, we talked about it depends on who is actually employing them. And if you're a firm, you're likely to be much more aggressive. And so if there's some nice cooperative one, actually you just want the best deal. And then we also talked about in repeated game settings, if you were in a community, maybe having some kind of reputation. So actually cooperation would be more important if you were likely to interact with the same agents, the same bargaining agents over again.
Okay, so bringing these two sides. One, the effectiveness at just getting good deals in some kind of measure like that, like we are measuring here. But also maybe if there was some reputation element that you were somehow viewed as a party that was negotiating nicely or reasonably or something like that, however you would characterize that. The back table?
I think something that came up was fits a bit with the second question that AI agents should be adaptable to be able to sort of evaluate things that are sort of outside the box. For example, you make a negotiation and it's not just maybe splitting a bunch of items, but maybe someone throws in an offer that you didn't expect. As a human, you can't assess that on the spot, but an AI agent probably should be able to assess outside the box splits.
Right. So if you're in this sort of outside the box, being able to consider consideration, this is a very closed assumption of this particular game, but in a more open-ended bargaining setting, this kind of adaptiveness. Yes.
One question that came up is in general, when we think in the context of LLM agents, they're always almost going to be fine-tuned to lower compute costs and lower latency, and that may predominate, right, as a reason to choose something that requires less of that computational cost. And so probably considering this part as the model, right, where probably those are hard-coded elements that they're going to prioritize ahead of the payoff.
So you also might care about the computational effort if you're going to be searching far and wide for a deal. On the other hand, depending on what you're making a deal about, it could be so important that the computation is negligible. Might depend on what the application is exactly. Finally, this table here, any thoughts on what you'd want a negotiation, what properties you would want them to have?
We talked a bit about, maybe fair, if we had, you told me that we had an agent that would be a fair negotiator. We said maybe you wouldn't want that necessarily if you had one of an agent negotiate for you. If, for example, I don't necessarily want the agent that's going to get the fairest outcomes. I want the agent that's going to get the best outcomes for me. So maybe there's a interesting discussion just about that, balancing those two, where if you assume then I'm playing against another agent that is making that same decision, not trying to come to fair outcomes, and you might not come to any outcomes at all. So there's we had a little bit of discussion about that. Maybe fairness isn't the best metric to maybe if you talk to get an agent to bargain.
So it sounds like you're talking about the same trade-off that came up in the other one about effectiveness for the individual versus some kind of reputation. Now, in a ideal world, and I think that actually a world that's similar to one we have, a negotiator is not going to just be making a one-shot deal, but there will be reputations that will matter. In my day job, I've had some opportunities to do a lot of negotiating, and I can tell you it's never a one-shot thing. I was the chair of my department, and I had the opportunity to hire lots of people, and I can tell you my goal was not to trick them into joining my university. You think that's not going to really work out, well, when they find out that you got me to agree to teach this much, and these people are only teaching that much. That wouldn't work. So the reputation almost always will be a factor. And how do we engineer our agent system so that they have these robust reputation systems that will help keep them on the cooperative path, I think is a really key thing. So thank you all for your contributions there. I think we can go to the questions. I'll just put up the conclusion slide here. There are things that I already said.
Yes, and we have a bunch of questions in Slido, and you can also upvote the things that you most want to see. But one question that came up was regarding this slide with the different mistakes that was made. Is it obvious that mistake 5 is a mistake, or do you think that the LLMs, or do the LLMs perhaps think that every game is iterated?
Okay, thanks. So the question is whether mistake 5 here is a mistake. By the way, who had that question, or who voted for that question? Okay, great. So 5 is a mistake if you believe the outside offer is, really represents that value. If you, if you were given an offer that would, actually maybe I need to explain the scenario a little bit more, because walk is different than just letting the time expire and not reach the deal. Walk says, I'm ending now, even though we have a few rounds left to discuss. And so you would never do that if the offer on the table was potentially better than the outside offer. Yeah, walk is different than making a counteroffer. Okay.
Yeah, and then another question here was, what were the biggest challenges in applying EGTA to LLMs? What are some of the most important open problems that remain?
Okay, challenges in applying EGTA to LLMs. So the reason is I find Slido is, what I really don't like about it is that it just removes the interaction. I like talking to Cecilia, but I also like to be talking to the audience. So who had that question about EGTA and LLMs? Okay, great. In a way, the LLMs, a big challenge is they're so kind of expensive to run, and getting a lot of data is a key thing. So one of the sort of technical questions in EGTA methodology is how to get the most out of the data that you have. Using a bootstrap for uncertainty quantification is one tool there. So you can make sure that you only collect the amount that you need to answer your questions with good enough confidence.
Yeah, and then another one on LLMs here. Do LLM agents differ from traditional moral agents in that LLM agents may not follow instructions well, while for moral agents, behavior can be ensured by the policy?
Okay, LLM agents versus MARL agents. Well, LLM agents have a policy, and MARL-derived agents follow a policy. Now, whether they're in accordance with instructions, I think, could vary either way, right? So if they're in this bargaining game, the LLM agent is just as subject to the rules. If if it doesn't follow the rules, it's viewed as a walk, and and so that has the consequence that it has. I think there's a certain distinction in how we analyze it and what kinds of questions come up, because when we're looking at the MARL algorithms, we are deriving different policies based on the game description, where for the LLMs we're sort of asking this question about what sort of organically is implicitly as policy, even though it wasn't necessarily trained there. We're hoping, and I did have a slide on some of the future work, is that we'll start looking at fine-tuning with the LLMs as a way to combine both the learning for the problem at hand as well as the trying to understand something about the organic behavior.
And then one question here is, did you try playing standard meta RL-based algorithms versus LLM-based metas?
So great question. Did we try the RL agents against the LLMs? Sort of yes and no. Yes, we tried, but we didn't. The RL in this setting didn't really work very well, so we don't really think it was a valid try. That's also ongoing work where we're going to try to get the RL right, so that. So by the way, so what I think will happen, frankly, I think the RL agents should be much better at this game than the LLM agents, but that will help us understand something more about where their weak points are. So I mean, in general, we find the LLM agents are not very good at strategic thinking. And again, maybe that's not surprising, given that maybe it's not how they were trained. They're very accommodating. Now, that differs among the different models, right? They kind of, RLHF sort of gets them to do things what you want. So sometimes we see player 2 will just accept whatever player 1 offers, no matter what, right out of the box.
We have one which is rising now also, which is how many equilibria do you think there are in the game?
How many equilibria are there in this game? In the full context, I mean, let me just say there's a space of equilibria, right? It wouldn't be because these are continuous sort of potential policies, so they're with stochastic action. So the counting them is probably not very informative. However, the question is sort of how are there major qualitatively different equilibria to this game? My guess is that there'll be some degenerate equilibria, where the agent that tough versus walk, or things like that will be kind of degenerate equilibria. But in the space where they're actually often getting deals, it's a question about whether there will really be very qualitatively different equilibria.
We are almost out of time, but I'll take one last here, which was someone who asking if the difficult problem isn't when you have more than 2 agents that are playing different algorithms. And what do you think about that?
Okay.
Yeah.
So, the main question was so we are competing amongst algorithms, right? And then we are treating it as a meta game where algorithms are playing against each other, where you already get the payoff. But what if there are more than 2 agents in a multi-agent game, and some agents are playing, let's say PBO, some agents are playing a different algorithm? That's much harder to evaluate.
So first of all, EGTA applies to any number of players, and we have techniques that help scale up in players, very well. We generally require, symmetry to scale up a lot, assumption of symmetry. One thing that's interesting about the metagame framework is that, notice the bargaining game is not, you could view it as non-symmetric because player 1 and player 2 are in different positions. Actually, the way we defined it, they just flip a coin at the beginning to see who's going to be player 1, who's going to be player 2. That makes it symmetric. But even if you had a game that was really not symmetric, the metagame is symmetric, at least under our assumption that the meta derives policies that could play any player in the game. And you can certainly come up with solutions that have different players choosing different metas those are in the space. Remember, we're estimating the whole payoff matrix that consists of all combinations of different mods playing against each other.
Yeah, I will have to cut you off there. A big round of applause for Michael Wellman.